Again, there's no mention here about what the frequency or W is. So I'm assuming in this problem, this circuit is built in the US, so the frequency is 60 hertz, 2 pi f, that's what W is, 2 pi times 6377. We'll see if that's the case. So when I change this to phasor, the impedance of an inductor is JWL. So that would be VS there's an inductor here with the value of, there's the dot here, J, W, which is 377, and L, which is what? 2 millihenry, that's 0.002. .377 times 0.002, 0.754 J. Let's get the other inductor. JWL, W377, and L is 5 millihenry, 0.005. 1.885. And the mutual inductance right here, JWL, J377, mutual inductance 0.003, 3 milli. J 1.131. The only thing I want to take a peek is figure, okay. I was looking at the circuit to see if anywhere in the problem they tell you what W is. Nothing. So just I'm assuming, again, we're using that value of W. And now this is I sub 1 going in here. And this is I sub 2. And now let's do, they want us to write two equations, one on the left side, one on the right side. So let's write an equation for the left side. The left side, here we go, let's start with this one. Again, let's not even look at this side. Pretend you don't see it. Let's write an equation for this. And that would be what? Negative Vs plus 3 times I sub 1 plus J 0.754 times I sub 1. Now let's look at the mutual inductance. The mutual inductance is going to be what? J 1.131 times I sub 2. And my only question is that a positive or a negative? And let's watch it. The mutual inductance, the effect of this current going through that on this one. That's why we use that current. Now, it's traveling this way, that current is going to mark the here plus, minus, which means the dot will be what? Positive. This will be minus. So when you travel this way, that becomes what? Minus.
So it's minus because the current in the
Well, you're traveling this way, we're marking it plus to minus, right? And notice the polarity of that one backward. So now if I clean that, I have Vs equals, the whole thing equals 0. If we take the negative Vs, that becomes a plus. What do we have? 3 plus J 0.754 times I sub 1 minus j 1.131 I sub 2. And we're not anywhere next to their numbers. They use 10j and 15j. So you're right, they must have used a different value for j, like a 5,000. Yeah. But nowhere in the problem it says use w to be that number. So either they forgot to write w equals 5,000 for that problem. And it doesn't refer to a different problem, does it?
Well, 13.2 had the same circuit, but then they didn't have omega value for that one. We didn't need it, but we needed it.
Actually, for 13.2 minus 1,000, that's 1,000.
Oh, it's actually
Yep,
1,000.
yep. So, but even if you use the 1,000 here, these numbers won't work. Because that number becomes what? 2j. So it has to be a 5,000 to make it a 10j here. That will make that 15j, yep. So w for this problem, actually, it's been used, assumed here, it's 5,000. Just looking at the answer here, w for this is really 5,000. Because if that's 5,000, this is what? 10j, that's 15j, and this one will be 25j. And notice that's a 25j. That's a 15j. That's a 10j. So that's what they're assuming here. W is 5,000, but there's nowhere in the problem was mentioned.
We can't see it all without pointing it.
Oh, here. I said if you look at the solution here, it says 3 plus 10j. The only way to get 10j if W is 5,000. 5,000 times 2 milli, that's 10j. It's going to make that 3 times 5, 15j. That's the minus. It's going to make that 5 times 5, 25j. So actually W for this problem is really 5,000, but there's nowhere in the problem it states that W is 5,000. Somebody forgot to write that in. You know. So that's why the answers don't match there. We'll finish this. We'll just write another one with my numbers. Now if we do KVL right here on this side, that'll give me what? Let's take just this one without paying attention to that. 10 I sub 2 plus j 1.885 times I sub 2. Now let's look at the mutual inductance. Let me bring here white out. Let's look at the mutual inductance. Notice I'm traveling this way, so I'm marking this what? Plus minus. I'm marking this plus minus because I'm traveling this way. Now let's see what happened to mutual inductance. The mutual inductance is going to be J 1.131 times I sub 1. And again, let's see if it's positive or negative. Addition or subtractions here. This current's traveling down this way is going to mark it plus to minus. So the dot is going to be what? Negative, right? That means the effect of the mutual inductance on this is going to be the dot's going to be matching minus and plus. And notice that's backward to this one. And if I clean that equation, I will have 0 equals negative 1.131j times I sub 1 plus 10 plus 1.885j I sub 2. So there's my second equation. Now I get two equations by two unknowns. For this, they just said set them up, don't solve them. But if you want to solve them, if you know what Vs is, you're done with it. Because we don't know what Vs is. But if you know what Vs, You have two equations by two unknowns, I sub 1, I sub 2, solve for 1, solve for I sub 1 in terms of I sub 2, use substitution, you get your answer. Yeah, that problem is missing something. Missing W to be 5,000 in it, to get the numbers they have on the bottom. Any other one? Notice we said actually the value of the mutual inductance, it's always less than or equal to the square root of L1 times L2. So when the two inductors right on top of each other, like sitting like this, where you get all the waves going through it, then they'll equal to that. Will be this equal to the square root of L1 times L2. But as you start to move away from them, not all the waves going through them, not all the fields going through them. So you're getting a portion of that, the value will get weaker and weaker, and soon enough as you go far away, the value will go to a 0. They're too far from each other. So that depends again on the value, because if you remember from just like magnet, you have current going through this. Let me take this one out. When you have a field, when you have an inductor like this, you have a field as the current going through it, it looks like this. You know? And it's going on both sides. Just like magnet. So if the other inductor is close to that, like right there, notice all these fields going through it. The value of M is going to be large. But if the inductor is far enough, like right here, the value of the mutual inductance is going to be small. There's only few actually of these fields going through it. If you go far enough, that value is going to be what? 0. You're not even close to that. So that's why the value of M is always, it's less than or equal to the square root of L1 times L2. Depends how far away from each other, what portion of these waves or fields going through it. And that's called the coupling coefficient, K. And K is actually equals M over the square root of L1 times L2. So if you ever encounter that, it's called coupling coefficient. And the definition of that, this is the degree to which M approaches a maximum value is described by the coupling coefficient K, and K equals M over. Now if it's equal to 1, you get 100%, and K between 0 and 1. So a large value for K when actually these inductors are very close to each other. And the value will be small when they're far away from each other. Now, a lot of people don't like to write the equation like this. When you have, let me go back to this picture. They said, is there a way I can replace these two inductors with an equivalent circuit? So let's look and see if we can find the equivalent of these two inductors. We're going to be looking at something called T and pi equivalence network. The reason they're called T, because you can replace it with the circuit that looks like this. We can replace the two inductors with a mutual inductance with something like this. That's called the T equivalent. Or we can replace it with the pi, which will look like this. Now let's take an example and see what will happen. Let's talk about the T equivalent. So I'm going to focus on this one. Let's see what will happen. If I have a circuit that looks like this, and this is L1, and this is I sub 1. This is L2, and this is I sub 2. The mutual inductance here is M. We usually use lowercase when we are in time domain, uppercase when we are phasors. So let me just change back this to small I. I1, like this. So this is V1 here, and this is V2. And there's my dot here, and there's my dot here. If I look at V1, if I don't switch to time domain, V1 is L1 di1 dt. What about the mutual inductance? The mutual inductance is going to be M di2 dt. Again, in this case, is it positive or negative? What do you think? Why positive?
They both match.
Yep, the current coming down is going to mark it plus to minus. That's the same as V1. Well, the mutual inductance is going to, so the mutual inductance is going to come down plus to minus. Notice the effect. It's going to be the same thing. The dots matching, that's a plus. And what about V2? Let's look at V2. That's the voltage here. It's going to be L2 di2 dt. And this will be again plus M di1 dt. So when you look at the circuit, that's what V1, V2 based on the mutual inductance. Now let me give you a different circuit. In this one, there is no mutual inductance. I sub 2 go in the same direction and just like this one, and I sub 1 is going the same direction like this one. And this is V1. And this is V2. And this is M. Let's use the value of this M Henry. Let's use this L1 minus M. And let's use this as L2 minus M. Can we find what V1 and V2 here from this circuit? Nothing to do with that. Let's look at that. Do KVL right here. Negative V1 plus, what's the voltage drop here? We take the inductor, which is L1 minus M, times what? The derivative of that, di1 dt. Plus, remember, I'm using V equals L di dt, right? That's what I'm using. What's the voltage here? The mutual inductance, M, times the current down. If this is I sub 1, I define I sub 1 is going in, right? And I sub 2 is coming this way. Notice it's going in. So what is I sub 2 here? This will be M times what? D dt of the current going through, which is I sub 1 plus I sub 2. Do you agree with that one? All of that equals to 0. Let's clean it. This will be V1 equals L1 di1 dt. This is minus M di1 dt, and this is plus M di1 dt. What will happen? Cancel each other out. So what's left? M di2 dt. And put this in a box. Let's do a KVL for this end. What is KVL for that end? Negative V2 plus, I'm traveling this way, it's going to mark it plus to minus, L2 minus M times the current going through, which is what? di2 dt. Plus the mutual inductance. What's the current coming down? d dt I1 plus I sub 2 equals 0. Clean that. That'll be L2 di2 dt. The M with di2 will cancel each other out. di1 dt. I'm curious here about something. Let me pull my first sheet out. I wonder what were the equations for this here when I did them. Let me fold this one so you get to see it. What's V1 equal to? L1 di1 dt plus M di2 dt. See it? That's the same as this. Let's look at V2. L2 di2 dt plus M di1 dt. What does that mean? That means this circuit that you see here, it's the equivalent of this circuit. This is equal to this. So if you don't like to deal with dots and polarity and all the stuff there, you go. Let me actually rewrite that by doing this. But this is equivalent to as long as the current entering the plus. If we change direction, we have to rewrite that one. Let's see what will happen if I change direction on that. Or do we have an explanation? There we go. This is the equivalent. I don't know if you can see it. It says, if either of the dots on the winding, the dots right here, can you see the dots here? I'll move it down here. If either of the dots changes here, either one, if they're both in the same direction, you're good because it's going to be the same. But if either of the dots in the winding of the given transformer is placed on the opposite side, so if you move this one down here or if you move this down here, the sign of the mutual term will be negative, which means, what does that mean? This M will have to be replaced with negative M. So basically what happens, since M is being replaced with negative M, this becomes L minus a negative M. What is L minus a negative M? This will be L plus M, this will be what? L plus M, and this will be what? Negative M. So that's what you have to remember. If one of these dots changes, this is L plus M, and this becomes negative M. Do we have a circuit for that? Maybe not. So just remember that one. So if I was trying to do the equivalent of this circuit, this is going to be L1 minus M. Notice the dots are in the same direction, so I'm good. Is going to be 30 minus the 40, which is what? Negative 10. This one here is going to be 60 minus the 40, which is 20. And this one will be the mutual value, which is 40. That's the equivalent.
So like in terms of like the one on top and the one on bottom, like if you would build it, like is there one you would prefer to build?
No, some people, well, not to build it. I mean, it's just in terms of analyzing. I don't think we have any negative inductors if you go to the lab there, right? So if you want to do that, so we have a problem with that, David, because we don't have that. Yeah. But in terms of analyzing it, some people probably prefer this one. I don't have to look at mutual inductance and all that. Just rewrite these and just treat them as just like any other inductors. So that might be a preferred choice for some people instead of dealing with that in terms of analyzing them. Now again, if the dots changes direction, then we have to worry about the values.
And like the distance between the inductors, are we dealing with like inches or like millimeters?
Well, if you look at them when you buy them, actually, yep, a lot of these look like this. See them? I don't know if you can see that picture. And there's actually one on the top, one on the bottom. That little gap between them, little tiny gap. There's two of them right here and this one too. So we're not talking about that far away from each other. Now some of them, they could be about the size of a cinder block. If you look on power lines, they're about the size of a cinder block. So you got one coil here, it actually goes around the core there, one piece here, one piece there, might be 2 inches, 3 inches between them. You know, but the farther you go, the weaker they become.
We used to make transformers at work.
You did?
The smallest one was about the size of that.
This one?
Nope.
This one?
The one, that one. There's two on there too.
Yep.
It's, you wind it over and then you put a piece of insulating tape over the first set of windings.
Then you put the other one over
And
it.
then you wind right over
Yep,
top
yep.
of that. And just that piece of insulating tape
Yep.
is enough to create the distance.
Yep. So we're not talking about like miles or feet or something, yeah.
But if you had those big giant cinder block ones, they probably actually have to be placed separately
Yeah.
so they don't interact, like
Well-
feet apart.
Well, you don't want it to be not interacting because that defeats the whole purpose, so.
Well, if you had
yeah.
two that
But-
were supposed to do their jobs
Yep,
on their
yep.
own, then you
Yeah,
would actually
that's
have
true.
to
If you want
mount
separate-
them far apart
Yep.
so that they wouldn't, because their fields would be much
Yep.
greater. So in order to have no interaction between the two separate units, you'd have to probably place them.
Couple of feet away, yeah.
apart. But like you were saying, inside, there's two that are probably only an inch apart or less.
Now, if you want to do the pi circuit a little bit more challenging, not challenging, but the calculation for it, it comes out a little bit different. This is really what the pi circuit will look like. See, this is the equivalent of a pi circuit. Look at the values. I don't know if you can see it. The value of the top one, yeah, the value of the top one is going to be L1 times L2 minus M squared divided by M. The value of the one on the right, this is LA, this is LC, you call them LB there. So this is the one on the, is going to be L1 times L2 minus M squared. The top is always the same for all three of them. But the bottom is not going to be M, it's going to be L1 minus M. The bottom here is L2 minus M.
So the top's the same for all three of them?
The top is the same, L1, L2 minus M squared.
Okay. Where's the L1, L2 coming in?
Well, that's when you have, this is L1, that's L2.
Oh, and then
Yep.
you would turn it into...
So if I have this circuit, L1, there's the dot, current coming in. This is L2, dot on the top, I sub 2 coming in. I can replace this with so this is like V1 right here, and this is V2 right here. So this is V1, this is V2. This is I sub 1, this is I sub 2 going in. I can replace this with L1, L2 minus M squared divided by M. That's the value of this one. This one's going to be L1, L2 minus M squared over L1 minus M. This one will be L1, L2 minus M squared divided by L2 minus M. So an example, let's take the previous one we just did. We had 30, 40, and 30, 60, and 40. 30, all millihenry. 60 millihenry. And 40 millihenry. I'm going to replace that with, I need a calculator here. Let's see what the values for them are. L1 times L2 minus M squared divided by M1. So this millihenry, 30, turn it on first, clear. 30 times 60 minus 40 squared. 200 divided by 40. This will be 5 millihenry. This one, we know the top is 200, so 200, I just did the math, divided by L1 minus M. L1 here is 30, 30 minus the 40, which is what? Negative 10. 30 divided by negative 10. 200 divided by negative 10. This will be a negative 20 millihenry. And this one will be what?
10.
Will be 200 divided by 60 minus 40, which is 20. 200 by 20, that's 10 millihenry. So that's the equivalent of this one. So instead of dealing with mutual inductance, you can drop it and use this one. Nope, come back here. So you can do a pi circuit, you can do a T circuit. And again, there's the equation. That shows you all the values for them. So maybe you want to keep that handy somewhere. Do the math. Notice it says, we may compensate for a reverse of either dot. Can you see that here? Let me highlight that. If any of the dot is backward now, it says, how do we do that? We may compensate for reverse of either dot. in the given transformer by merely changing the sign of M in the equivalent network, also just as we found in the equivalent T. So M becomes a negative M. Well, here's what's going to happen. When you square it, it's not going to affect the top. Right? When you change M to a negative M, you square it. Is that going to change your answer? No. The top is going to be the same. But what happened in the bottom, this becomes what? L2 plus M, L1 plus M, and this becomes a negative M. So you replace M with the negative M, and that will take care of it. So just highlight these, yep, right there and right here. It says the same thing.
The dots in place.
Only one dot at a time, because they have to be matching. So if one of the dot changes, like meaning if this one moves down or this one moves down, you can still use that, but you're going to replace M with negative M.
Is that the same effect as if the current switched directions?
Correct, correct. Yep. A lot of times to deal with that, what they do, they didn't discuss that here, because what you can do, Tom, when you have current going in, you can just reverse the direction of it going the other way and use a negative value for it. So that's what they do. Yeah. So here you got to find color problems. Here again, you multiply L1 times L2, you multiply these guys. Oh, that's the equivalent value actually. They already did that for us. Okay. Now, we've been talking about transformers, but none of them are really ideal transformer, but we can cheat every once in a while and treat the circuit as an ideal transformer. It is a useful approximation. It's not really a true value, because in real life there's no such thing as ideal one. Ideal means the wires have zero resistance in them. The coupling is 100%. So it doesn't work. A very tightly coupled transformer, very tightly coupled, in which coupling coefficient is almost 1. That's what an ideal transformer uses. We said all the fields, you get both coils, you get all the fields going through them. K is almost a 1. We neglect the resistors through them. If you have an ideal transformer, you can use an approximation for that. That makes the math a little bit quicker, and your answer is not going to be much off there. You'll see the math will be like boom, 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 and you're done with it. No more transformation, none of that stuff. Again, what's an ideal transformer? It's a very tightly coupled transformer where K is almost a 1. And it says, okay, if you look at it, the second inductive reactants are extremely large in comparison to the terminating impedance. Now, what happens when you have an ideal transformer, the way you differentiate between them on a piece of paper, because you have no idea if that's ideal transformer or not, the way we draw them, notice these transformers, you have the dots, and that's it. Ideal transformers, when we draw them, we put these two lines in between them. When you put the lines between them, that tells you that's an ideal transformer. The other thing you'll notice about when you're dealing with ideal transformer, they give you the ratio of the number of turns. As Tom said, he used to design them. He'll take the wire, wrap it around the first one, and they'll count how many turns. They'll go 1, 2, 3, 4, 5, 6, 7, 50, 200, 300. Then they put a little wax paper or something to separate them, put the other one, count how many turns around that. Here we need to know the number of turns, N1 to N2.
So a transformer is just two inductors next to each other?
Yep, two actually, we take wires, wrap them around, and the space between them, we take the other one wire, wrap around, and that's what you have there. If I can take actually...
An inductor is just a coil of wire.
So a transformer just refers to both of them next to each other?
Yep.
Yeah.
If you take, if you go to the lab, when you go to the lab, I wish I was in the lab, but if you go to the lab, ask Barbara to do this. Take a battery, actually. We said if you take a nail here, and you take the wire, right, this is a nail here, and you take the wire and you wrap it. what happens? So that becomes a magnet, right? Now if you take another wire and wrap it here, and you measure the current through this, it's not even attached to that. If you take and measure the current, you will see there's a current going through that. Why? It is close to this. And you'll see that value changes on how far you move it. Bring it closer or farther from each other. You don't have to put that, but just take another one. Wrap it. A lot of times, actually, to make it work even better, we take a core, like we call the core, which is a piece of metal like this. And the first inductor will look like this. And the second will be wrapped around this piece. That's what you have. And actually, they do that in physics. I don't know if you did the physics, anyone physics too? You probably built that one in physics. Did you build it?
Not in this physics, but in high school physics I did.
In physics 2 here, they try to build it, and they have different actually pieces. They put a piece of metal and watch the value changes. So that's the core, this one right there. And this is the number of turns on this, we call it N1, the number of turns on that one, N2. And based on how many turns you put there, it affects that one. It affects the voltage and the current going through that. There's a relationship between them. So this would be V1, this is I sub 1, this is V2, this is I sub 2 going in. We might have a picture, a nice picture here in the book, maybe, maybe not. I'm just looking to see if I have a picture transformer, like open. I wonder if I can find something on Google.
Google has everything.
Let me just quickly, I don't want to leave the camera running for nothing,
Are
but
those both I1 and I2?
yes, I1, I2. Well, I'll keep looking while I'm writing stuff down, just don't want to leave the camera running, nothing on them.
Video has gone on for a while now.
Huh?
Your video has gone on for a while.
Oh, yeah. It's all right. I think it's been okay lately, you know.
I've seen videos on YouTube that are like 2 hours long.
Let me stop this.